All right, so you have tests in your hand. Flip to number 7 real quick. Okay, so 3 to the 2x minus 4 times 3 to the x, so just 4 of it, 3 to the x, plus 3. Might help to, think of these sort of grouped like that. The 3 to the 2x, it might help to think about it this way, that's the same thing as 3 to the x squared. So this is a case where, because those are the same, right, those 3 to the x terms, we can treat this thing like it's quadratic, right? Quadratic is sort of, in like form or in shape. Use the structure of the thing first, because we can't combine the 3 to the x terms, right? Because they're, one's 3 to the x, there's 3 to the 2x, or 9 to the x if you want, but you can't really get anywhere with that. You can't multiply these because it's not 4 times 3, it's 4 times 3 to some power that we don't know, right? So there's no way to combine those middle terms. But again, we can treat it like it's quadratic, just, quadratic that's like, t squared minus 4t plus 3 or something, right? Or, I usually just do this thing instead of an actual change of variables. But the thing to do here is to try to factor this or use quadratic formula. Things that multiply to 3 and add to -4. -3 and -1 would work. Or again, quadratic formula is fine. And then you're just factoring it in terms of this, right? Okay. So you end up with something like that. But then once you've got it factored, again, this is a product that's equal to 0, right? You're multiplying there, getting 0. That means you can split these up. And when you split them up, you end up with a couple of, small, straightforward exponential equations to solve. If 3 to the x equals 3, you can write this as, the log base 3 of 3 if you want, or if you see that that means x has got to be 1, then you can just jump to that, right? 3 to some power equals 3. Okay, well, the power will be 1 then, right? Or, take a log and evaluate it. The other factor, you get 3 to the x is 1, which means that x is, well, again, the log base 3 of 1 if you want, or if you see that it's just 0, you can just jump to 0. Okay, that was the one that, just about everybody had some kind of issue with, and a lot of times it was just even like where to start. So that's the main one that I wanted to talk about. Does anybody have any questions about any of the other ones? Anything else from the test we want to look at? All right, well, y'all, take some time to look over it, and if there are things that you want to talk about, over the next couple of days or whatever, send me an email and let me know, and I'll see what I can do to help. I have obviously handed tests back. I haven't updated grades yet, so I will do that after my 9 o'clock class. I'll get grades updated so that you can see kind of exactly where you are overall. If you have any questions or want to know anything about that, just let me know, and we can talk about that. Okay. All right. Other stuff at this point? I did look up and confirm that the final is Monday the 12th at 8 o'clock. So again, I'll remind you about that several hundred more times between now and then. But all right. So we left off right here yesterday. Solving this system. I told you to go do it. You went and did it, I hope. Tell me what we should or can do here. Okay. What do you want to eliminate? X or Y? X? Okay. Let's eliminate X. Again, I just, want to kind of plan ahead a little bit, and I'm trying to kind of be deliberate about, saying, okay, here's what we're going to do. We're going to eliminate X. That's our plan. To eliminate X, one equation has just one X in it, the other's got -2X. So I'm going to need to scale one of them to get those coefficients to match, right? So what do we do? Multiply the first equation by 2, which would be 2x minus 4y equals 8. The other one I'm just going to copy over, -2x plus 4y equals -8. Okay. If we're trying to eliminate x, now the coefficients line up, right? 2x and -2x. To get x to drop out, we would need to add or subtract. Same value, opposite sign, so we need to add. 2x plus -2x is 0, which is good. And then we just do the same thing the rest of the way across. -4y plus 4y is also 0. And then 8 plus -8 is also 0. Okay, so this was the other place where we looked at this one at the end of class yesterday at 7, and we got a weird thing that didn't make sense, right? 0 equals 2, a thing that is, just logically untrue, right? And we looked at the graph and we saw parallel lines. We decided, oh, well, it doesn't have any solutions because they're parallel lines. So they're going the same direction, but they're apart from each other, which means they never intersect, right? They never cross. Now we also get a weird thing happening, but now it's a weird thing that's true, right? That's sort of like vacuously true. It's a tautology, right? It doesn't matter what X and Y are, as far as I can tell here, X and Y are gone. I get 0 equals 0. What does that mean? Maybe look at the graph. X minus 2y equals 4. Yeah. What was it? -2x plus 4y equals -8. There's one. There's the other one. So what's happening? They're the same line, right? They're the same line. They're just, kind of disguised a little bit, right? Excuse me. One of them is, scaled by 2 or by -2. If you took both of those and solved for y, you would get exactly the same thing, right? So they have the same slope and the same y-intercept, which means they're exactly the same line. What does that mean about this system where solutions to a system are points that the two lines have in common? That they're infinitely many, right? It's not just a single point where they cross, and they're not parallel where they don't cross at all. These sit right on top of each other, right? They're the exact same line. So every point along that line is a solution to the system, right? We have to be a little bit careful here because that doesn't mean that everything is a solution, right? Like this point up here, that's not a solution to the system. But this one is, and this one is, and that one is, and all the points that are along the line are, right? Because any coordinate pair, like that one, for example, or that one, or any of the other ones in between, are going to satisfy both of those equations at the same time because that's why they're on the line, right? So what we do here, so these are the same line, which means that there are infinitely many solutions. To handle the fact that there are infinitely many solutions, but they're still kind of specific points, right? It's still a specific set of points that solve this thing. We can say something like this: infinitely many solutions where solutions have the form Excuse me. And what we do here is basically write out the equation of that line, right? So if x minus 2y equals 4, that means that x is 4 plus 2y, right? Excuse me, geez. So I can write all of the solutions like that. Or you could solve it for y. So y is positive 1/2 x minus 2. So you could write the solutions as x comma 1/2 x minus 2. Like either of those would be fine. Those are equivalent things. Basically, all that we're trying to do is show how you find a solution, right? There are infinitely many of them, but that doesn't mean that every single point in the whole plane solves the thing. It still points on the line, right? So what this does, or this first one says, if you give me a y value, this thing is going to find the x that goes with it so that you land on that line, right? So if you tell me that y is 3, well then 4 plus 6 of 10. 10, 3 is a point on that line. Or this is the same thing, but parameterized with x instead of with y. You give me an x value, 1/2 x minus 2 is going to generate the y value that goes with it that lands on that line, right? So I wrote it out both ways because the way that these are set up in my math lab and the homework, it's going to have like, if I remember right anyway, there are like, an A, B, and C, like answer choices. There's one solution at this point, you type in the coordinates, or there's no solution and it's inconsistent because they're parallel, or there are infinitely many solutions. If you choose the infinitely many solutions one, it's going to have like a place for parentheses for a point, right? But it's going to have like x comma blank or blank comma y, right? Where you're looking for this basically, right? And I think some of the problems are set up so that it gives you x and you tell it what y would be. Some of them are set up so that it gives you y, you tell it what x would be, right? But again, either way, it's just solving for y or solving for x, right? I think I pointed at the wrong things when I said that, but that's kind of how you would do that. Does that make sense? Yeah, okay. I know that part's a little bit weird, but again, it's basically just, what does the function look like, either from y's perspective or x's perspective, so that you land on that line. Okay, so those are kind of the two, sort of weird cases for linear stuff, right? You either get two lines that sort of don't have anything to do with each other and intersect once, and that one intersection is the one point that they have in common. That's the one XY pair that solves the system. So that's kind of like, what we expect, right? For like a typical problem to look like. Or you get parallel lines that have no solution at all. Or you can have, do it this way, two copies of the same line, but, kind of disguised so that you get infinitely many solutions. All right, so one unique solution or no solutions at all, or infinitely many. That's kind of what can happen with two linear equations. Okay, everybody good? Do you have any questions about like how to do the substitution or elimination stuff, or we feel pretty good about that? Yeah, okay, cool. So the other thing that we're looking at in 7.1 is doing all the same stuff, but with things that are not necessarily straight lines. So all we're going to add here are things that are nonlinear. So we might have something like this, where you've got a straight line and whatever this thing is, right? X squared plus y squared equals 9 is actually a circle. So this is a straight line and a circle. Well, thinking about like what that would look like in the plane, if you've got a straight line somewhere and a circle, intersections are still what we're looking for when we talk about solving the system. But if you're talking about a straight line and a circle, there's kind of more possibilities to what can happen, right? So that circle looks something like that. It's got radius 3. I don't know why I'm being so. There we go. Okay. Well, whatever. Like, it's fine. Who cares? If you take that circle and intersect it with a straight line somewhere, right? We could actually find the line, but let's just think about, possibilities. How many solutions could we get? You could have 2. Can you have fewer than that? Could you get just 1? Yeah. There's 2, right? What if the line sat right like that, tangent to the circle, right? Just brushed up against it at one point. That would just give you 1 solution. Can you have none? Sure. What if the line's over here? So there's kind of more that can happen, right? And it's going to vary more from one problem to another, right? So you're going to, see some stuff here where we're talking about, like, look at number 2. That's a parabola and a circle. Okay, well, parabola and a circle, there's kind of a lot of ways that those things could sort of interact, right? So there's more going on there. And the other thing is that we're a little more limited in how we can approach it, right? For linear stuff, the stuff we did yesterday, and hopefully you saw this when we worked through the practice problems, you can do substitution or elimination whenever you want. It doesn't matter. Sometimes one's a little bit easier. Sometimes one's a little bit harder, whatever. It always works. That's not true here anymore. Can you do elimination with this? Can I add or subtract those together in a way that's going to make something go away? No, because x and x squared are not like terms, so you don't combine them if you add or subtract. Y and y squared are not like terms, so you don't combine them when you add or subtract. That means elimination is not going to work here. That means I have to do some kind of substitution. On the other hand, here, adding or subtracting these, x squared and x squared, those are like terms. So I can subtract and get those to combine and to drop out, right? So I could do that here. I could do a substitution instead. Like I have some options there, but you're only going to combine like terms, right? So we're still using substitution and elimination. But we need to be careful to only combine like terms. Now for the substitution part of it, everything that we did yesterday, we like took the thing and solved all the way for, y or x or whatever, right? The thing that you're really doing there is replacing, like for like. So I could take this, for example, the second one. I don't necessarily have to solve for x to do a substitution. I can solve for x squared and use that to substitute in the other one because the other one has an x squared, right? You just have to be substituting a thing for the same thing in the other equation. The rules, the idea is still the same. You want to, use one equation to find a thing and plug it into the other one. Again, you just have to be replacing a thing with the same thing. Okay, so let's take a minute, graph those things. I would just throw them in Desmos because it's going to be a lot easier to graph them. But graph those things and sketch it and see what you find in terms of solutions. it's not mine. Definitely almost drank this water bottle that's just been sitting up here for a couple of weeks. That was never mine. Okay, so the first one, we're looking at a circle and a straight line. So how many places do you see where these intersect? 2, and they are 3, 0, and 0, -3, right? Okay, the second one, x squared minus y equals -1, and x squared plus y squared equals 5. I should have turned some of those things off. Second one is these two things, right? X squared minus y equals -1 is a parabola, right? Y to the first power, x to the second. So that's a quadratic function, right? It's just in a different order than we're used to, but that's a parabola. X squared plus y squared equals 5 is a circle, circle with radius sort of 5. So that looks like this. They intersect twice. The intersections, so the solutions to the system are 1, 2, and -1, 2, right? Okay, so we've got solutions, so we know kind of what we're looking for. Let me just copy those over here real quick. So 3, 0, 0, -3. That one was something like this. And something like that. Okay. Now, let's look at how we would actually solve those systems. So it's the same thing, right? So we know what the answers are. 3, 0. 0, -3. Let's take a look at the actual system. X minus y equals 3. X squared plus y squared equals 9. What can we do? Same rules as yesterday. You can multiply or divide by a constant if you want to change coefficients, right? As long as you do it on both sides. You can do that to one or both equations. And then you can substitute, you can add or subtract the equations together. Do not try to square or take square roots or get into any of that kind of stuff because it's not going to do what you think it's going to do, probably, right? Like a square root does not help at all here because the square root of this is not x plus y, right? It doesn't apply. It's a multiplication thing. So over addition, it doesn't, hit it just term by term like that. So what I'm driving at really is that elimination is not going to be an option because adding or subtracting these things together, you don't have like terms, so they're not going to combine. There's no way to make them like terms because you don't want any part of trying to take a square root of this or of squaring that because it's not going to do the nice thing. So let's look for a substitution. First equation has x minus y in it. The second equation has x squared plus y squared. If I'm going to look for a substitution, which one should I use? The first one, right? First one's going to be a lot easier to solve for x or for y in a way that I can substitute into the other. All right, so take that first equation. You want to solve for x or for y? Doesn't matter. It's going to be the same here either way, right? So do you want to do everything in terms of x or in terms of y? Okay, so let's solve this for y then. Y equals, let's see if I add y over and then subtract 3, x minus 3. Then that is going to go here. Again, when you do that substitution, you do have to go to the other equation, right? Because again, we got to take these two things and sort of tie them together. So x squared plus, in place of y, I'm going to put x minus 3, because I just figured out that y is the same thing as x minus 3. So this is the second equation with x minus 3 substituted in for y. Again, at that point, after you do the substitution, this should be a thing that's just in terms of one thing we don't know, right? It's an equation that's just in terms of x, which is good because we know how to solve that. I'm going to expand the power there. X squared minus 6x plus 9. This is quadratic. A lot of these are going to end up being quadratics to solve, just because a lot of the stuff that you're going to see is quadratic because we know how to solve things, right? It's not that they have to, it's just that's a thing that we know pretty well. So I'm going to move everything to one side and combine like terms. 2x squared minus 6x. Subtract 9 from both sides, so equals 0. You could do the quadratic formula there. Since c is 0, it's pretty easy to factor. Also, you can just take out a common factor. So either x is 0 or x minus 3 is 0, which means that x is 3. Just like the stuff we looked at yesterday with the linear systems, once you get one of the things, right? So once I have the x values, you're just going to plug back in to get y. So getting to this part is the hard part. Now I've got x equals 0. I'm just going to go back and plug in to find the y that goes with it. Again, you can kind of plug that in, wherever you want to. Since we did a substitution, I've already got a good place to do it, right? I know that y is x minus 3. So if x is 0, then y is 0 minus 3. So y is negative 3. If x is 3, then y is 3 minus 3, which is 0. So our solutions are those two ordered pairs. X equals 0, y equals negative 3. And x equals 3, y equals 0. Again, not the only way you could do this thing. You're pretty much limited in this problem to doing a substitution. You could solve for x instead of y and then just do it the other way around. Like, wouldn't really end up being any different. You still get a quadratic to solve. In terms of y, you solve it, you get the thing, plug back in, and you got your answers. Okay? Any questions about how any of that works? You okay about that? Okay, so again, same idea as stuff we looked at yesterday, just sort of a little bit more of it, right? A little bit more important to think through how we start, right? How you're going to approach a problem, and then the solving part is probably going to be a little bit more involved because it's not linear, probably. Okay, so why don't you guys try number 2 then? That up there in case you want to look at it. Go into it the same way. Look for what you can do. Think about if there's anything that wouldn't work, and then do something. there are a few different ways there that, would all be pretty good options. Yeah. Yeah. Okay. Then just solve that. It's quadratic in terms of y. Get all the y's to one side. Factor quadratic. All right, what do you want? What do you see? What do you want to try? Okay. Elimination, it would have to be the x squared terms, right? Those are, you've got like terms in both equations, so we can't eliminate those. They're already, they already have the same coefficient. It's x squared in both, so we're just subtracting the two equations, right? So I can just do that right off the bat. X squared minus x squared is 0, which is good. That was kind of the whole point. Negative y minus y squared. Those are not like things, so we're not going to combine them, but it's still negative y minus y squared. Then negative 1 minus 5. Again, the sort of check in the middle is that this thing should just have one unknown, right? It should just be in terms of either all x or all y. This is just in terms of y, so we're good to go. That should be an equation that we can solve. It's quadratic in terms of y, so I need to get everything to one side. I would also rather not have to deal with the negative leading coefficient, so I'm going to move this over and move this over. So we've got y squared plus y minus 6 equals 0. That'll factor, but just for the sake of doing it, let's do it with the quadratic formula real quick. Does it feel to me as though something's not going to go the way I want it to here? If I goose something up, no. Okay. All right. B squared minus 4 times A times C would be negative 24 over 2. So negative 1 plus or minus the square root of 25 over 2. Again, that factor is perfectly fine. I'm just trying to, mix things up a little bit. So we're doing it both ways. Negative 6 over 2 and 4 over 2. So negative 3 and 2. Oh, I see. Okay, so those are y values. Now, if I take those and plug them in, if I plug x equals negative, or sorry, y equals negative 3 into this first equation, you get x squared minus negative 3 equals negative 1. So x squared plus 3 equals negative 1. So x squared is negative 4, right? But can x squared be negative 4? Like, can that, does that work with a real number? We're talking about solutions, intersections of graphs, right? Intersections of things in the plane. So we only are interested in real numbers. That's not real. That's the only thing you get from y being negative 3. So y equals negative 3 doesn't actually tell us about, places where these things intersect. On the other hand, if y is 2, then x squared is 1. And so x is plus or minus 1. Right, taking the square root of both sides. Well, if x is plus or minus 1, that means that the solutions that I get from that are, I'm writing in a place where you can't see it, is that positive 1 goes with 2 and negative 1 goes with 2. So 1, 2, and negative 1, 2. Y equals 2, x is positive 1 or negative 1. That's 2 points. So we do have to be a little bit more careful also with like how we actually handle the solutions, right? You can get a thing that appears to work for one of the values right here. I had a y value that shows up like it's going to work, but when I plug back in to find the x that goes with it, doesn't actually go anywhere. And if you had plugged into in case you're worried about it, if you plug negative 3 into this, the same thing would happen, right? Plug into the other equation. You get the same thing. X squared equals negative 4. Well, no, it doesn't. So that doesn't actually go anywhere, right? So it's not that just one of them works. Neither one does. But the other one, y equals 2. I get 2 x values. That means really there are 2 points there. Okay. Other questions about stuff so far? Okay. Let's do one more then together. don't know. About 8. It's got some options. Or, I don't know. Y'all tell me, what looks good here? How about 4? Let's do 4. So this is a circle and a hyperbola. That's this thing. I don't expect you to know what hyperbola is. At this point, if you go on a pre-cal, you get to do a whole bunch of stuff with hyperbolas there. But it's a circle and hyperbola. All I'm really interested in is like, I plug this thing into Desmos. Here's the graph. What I'm interested in are the places where these intersect. It looks like there are 2 of them right here, right? What can we do to solve this system? What do you see? Substitution, elimination, what do you want to do? Yeah. Okay.
We can multiply by 2.
Okay, multiply this one by 2, which would get rid of the x squared terms. Okay. That would work. Anybody see this? Same thing. Okay. Yeah, you could eliminate y if you multiply the first one by 3. You could take this first one and solve for x squared and do a substitution, right? Because there's x squared in the other one. You can substitute a thing for the same thing, right? So you don't have to go all the way down to solving for x. You can solve for x squared and use that to substitute if the other one has the same thing in it. Okay, so 2x squared plus 2y squared equals 8. And 2x squared minus 3y squared equals negative 12. To eliminate x, we need to subtract. Yeah. Got rid of the y.
If you multiply 4 by 3,
Uh-huh. Yeah, okay, let's do this real quick and then we'll look at that too. So if I subtract these, that's 0. 2y squared minus negative, so plus 3y squared, so 5y squared. And then 8 minus negative 12, so 8 plus 12 is 20. So y squared is 4. So y is plus or minus 2. Once you've got y, plug back in, find x. Like after that, things should be, kind of downhill from there. Let's take a look at doing the elimination the other way because Colby brought it up. Now, the thing that you want to be focused on, you're right that, if you multiply that by 3, it is going to be 12 and negative 12. But the thing you want to be focusing on is the thing that you're trying to get rid of, right? So that's where the 3 comes in. So if I'm trying to eliminate these, I'm going to multiply that by 3, which would be 3x squared plus 3y squared equals 12. Again, if I'm getting rid of y squared, I'm going to add. So that's 5x squared. The y squared terms cancel. And then 12 plus negative 12 is 0. Right? So x squared is 0, which only happens when x is 0. Now again, either way, you're not done, right? You have more work to do. This isn't, I'm not saying do both. I'm saying, here's what, that will look like either way. Now you have X, go back and plug in to find Y, right? I would plug in the place where it looks like it's gonna be the least amount of work. If X is 0, then first equation says Y squared is 4. So Y is positive 2 or negative 2. So you get 0, 2, and 0, negative 2. Here, if Y is positive 2, this is 4, so X is 0. If Y is negative 2, this is 4, so X is 0. Right, so again, you get those 2 points at 0, 2, and 0, negative 2. Okay? Yeah, so that's what either version of that elimination would look like. Just for the sake of doing it, let me, let's take this and solve for Y. And then substitute it. So 2x squared minus 3. In place of y squared, I'm going to put 4 minus x squared. So 2x squared minus 12 plus 3x squared. And, at this point, I'm just doing solving things, right? I just want to show you what the substitution looks like. Because this has a y squared in it, because this has a y squared in it, I don't have to solve for y, I can solve for y squared and use that to substitute, right? You just have to be substituting a thing for the same thing. Okay. So, if these had all been x's and y's rather than x squared and y squared, then this would have been, the same kind of thing we looked at yesterday, that you kind of have a bunch of options, right? There are a couple good ways you can do an elimination. There are a couple good ways you can do a substitution. The same thing is true here. It's just that because they are all squared, when we actually get to the solving part, we might need to be a little bit more careful, right? You take a square root, you get a plus or minus. If it's a quadratic that you need to factor, use quadratic formula, you got to do that. We're probably dealing with more than one solution, so we got to just be careful about how we handle all of that. Okay. Okay, cool. All right. Well, that's all I got. Hope you guys enjoy the